Now let's take a look at a practical application for composition functions. The problem we're looking at here is a common one, and it's quite possible you'll get something like this or very similar on an exam or quiz, even if it's just for bonus points, so it's worth covering here. However, this is a long problem, so you'll usually only get one aspect of it, but it's good to go through the whole thing as a mental exercise. Let's say we have a cylindrical container, and starting out, it contains 500 milliliters or cubic centimeters of water, and we know that it's filling at a rate of an additional 100 milliliters per second. So all we have to do is fill in the number of seconds, and we can calculate what the volume would be at any given time. But what if we wanted to know the height in the cylinder? Is there any way we can calculate that without having to measure it directly? So the problem here is a 5-part one, and it addresses just that question. So first we're asked to write the formula of the volume in the cylinder after time t. Then we're asked to write a formula for the height of the water in the cylinder in terms of the volume. We're then asked to find an expression for the composition of h of v of t, or height of volume with respect to time. Then we're asked about what this expression means. And finally, we're asked to calculate how long it takes for the height of the water in the container to reach 50 centimeters. So addressing the first part of the question, we're asked to write a formula for the volume in the cylinder after t seconds of time. If we let time equal x, then for any number of seconds we start with 500 milliliters of water and add an additional 100 milliliters every second. So we could write this v of x is equal to 500 plus 100x. Next we're asked to write a formula for the height of water in the cylinder in terms of volume. To solve this part of the problem, we need the volume of a cylinder. Just like for cubic measurements, cubic centimeters for example, we calculate the area of the base and then we multiply that by the height. We do a similar thing for a cylinder, except for the area of the base is the area of a circle, or pi r squared. So based on that we know that the volume in the cylinder is equal to the area of the base, which is pi r squared, times the height. We've already found a function for the volume in a cylinder after time t, and we have a formula for the volume of a cylinder as it relates to height. So what are the two common variables between these two equations? Well, it's the volume, right? And what we're trying to find from the volume, which we can calculate, is the height. So if we divide both sides of this equation by pi r squared, then we get volume in terms of height. So we have height is equal to volume divided by pi r squared. I think you get an idea of where this is going. We're asked to find an expression for the composition h of v of t. Since we're trying to find something we don't know, which is the height, based on something that we do know or can calculate, which is the volume, finding h of v of t will give us the height after a certain amount of time. So if we take the formula for height and we say h of v of t, then for the height formula, wherever we have a v, we fill in v of t. And that gives us 500 plus 100t all over pi r squared. So we've just figured out a way to determine the height in the cylinder after a certain amount of time without actually having to measure it. And so the final part of the question asks, how long does it take for the height of the water in the container to reach 50 centimeters? Well, if we rearrange this equation for the time by multiplying both sides by pi r squared, subtracting 500 and then dividing by 100, what we end up with is the time it takes to reach a certain height is equal to the height times pi r squared minus 500 divided by 100. If we fill in 50 centimeters for the height and calculate this out, the answer we get is 65 minutes, or approximately 1 hour. And we've just shown how composition functions can help us solve real-life problems. Okay, let's break here. When we come back, we'll cover translating and reflecting graphs of functions.